Hi there, welcome to your next unit. Today we're going to start by talking about what a constant rate of change is. Now it's possible you might have heard about a constant rate of change as what's called a K value. And K is essentially, if you remember from maybe your lesson before, is what we call y over x. So these things are all going to be kind of tied together. So y over x is going to lead us later on to what we talk about, which is going to be a slope of a line. And this all leads to helping us kind of understand how do we take a graph and look at a line like this and determine what is that slope, what is that value of the rise over the run. That means how much we're going up and down each time in order to continue that line. For a constant rate of change to take place, you have to have what's called a linear relationship, which means it's actually forming a line and that is linear, and it kind of goes the same way. So for example, if I had a graph that went like this, that's not making a line. I'm not going to find a constant rate of change with a graph that looks like this. To have a constant rate of change, you're going to form a linear relationship, and that's going to show you that you have points that form a constant line or a constant rate of change. A rate of change is a way of talking about how much its value is kind of going up and over again and again on a graph. Okay? Now sometimes we take our data and break it up into a T-chart like this. When we do this, essentially the first column is often our x value and our second column is our y value. We could talk a little bit here if we wanted to about dependent or independent and dependent values. Oftentimes this is our independent value, which means nothing you can do to it's going to change it. But this one here becomes our dependent value, meaning that whatever happens here is going to have an effect over here. And so oftentimes our y is dependent upon the x. So these are terms you might have heard at some point when looking at slope and talking about constant rate of change or that K value. Again, depends on what your classes taught last year, but these are all things you might have heard and they all blend together, and so we're just kind of starting off today with the first step, which is the constant rate of change. Okay, so relationships that have straight-lined graphs are called linear relationships. The rate of change between any 2 points in a linear relationship is the same or constant. A linear relationship has a constant rate of change. So here we see the height of a hot air balloon after a few seconds is shown in this table here. Determine whether the relationship between the two quantities is linear. If so, find the constant rate of change, and if not, explain why. And what we can see is after 1 second, the hot air balloon is 9 feet in the air. After 2 seconds, it's 18 feet. So what we can see on the left side is that we're increasing by 1 second, and the height is increasing by 9 feet. If this is linear, then that same pattern of 9 feet every 1 second, 9 feet every 1 second is going to continue as we go down the chart. And we can see that as we go up 1 more foot, we also go up 1 more second, it goes up 9 more feet. And again, 1 more second, 9 more feet. Because this rate of change is a constant, then we would say that this is going to be a linear relationship. And you could actually, in a sense, you could graph this, and if you had it here and it has time as 1, 2, 3, 4, you would have a line that would look something like this, and this would be at 9 and 18 and 27 and 36. You'd have a nice constant line starting at the origin 0, 0 to form a nice linear relationship there. Okay, so because the rate of change is constant, it is a linear relationship. Now that rate of change is always going to be the y over x value. That is our k, our constant rate of change. It's kind of k is a k and constant is a c, but that's kind of how that works, is y over x. So in this case here, it's 9 feet over 1, or 9 feet per second. That becomes our slope, our constant rate of change, and because it's constant, it is a linear relationship. That's what we're going to be determining with the other equations today. So let's take a look at some other ones and see if we can determine whether it is linear and what that rate of change, constant rate of change, might be. Okay, so in this case here, this becomes our x, and this is our y, and we can see here that as we go up 1 card plus 1, what's happening here? We're increasing by the difference between 3 and $1.50 is $1.50. So we're adding $1.50 by moving from here to here. So if I go up 1 more card, am I also increasing by here by $1.50? what is 3 plus 150? Well, it's 450. So again, that looks good. But you do want to make sure you check every value in the table. So again, we're adding one here, adding one here. Is this also 150? 450 plus 150 is indeed $6. So yes, indeed, we're increasing by $1.50 every time we maybe buy a greeting card. It costs $1.50 more. Okay, so our rate here becomes our y over x, or in this case here, $1.50 over one card. That becomes our constant rate of change. Okay, and it's proportional because it's kind of going up the same rate here. Let's look at number 2. Here we have the party table rental. The cost per table, we're looking at the cost per table. So we're looking at cost per tables. What we want to find out, is that a linear relationship? Does the amount of tables that I have a bearing upon the cost? Okay, so if I have one table, it costs me 10 out of 1. Okay, that's my rate in a sense here. I've got 10 over 1. So if I go up by 1, increase by 1, how much does my cost increase? Well, 10 to 8 is plus $8 more. Let's see if it continues. If I add one more table here, what's my increase there? 18 to 24, well, that's going to be a difference of $6. Now my cost went up by 6. So already we can see this is not going to be linear, is it, right? My cost is becoming less, actually. If I add one more table, now what's my cost? It costs me $4. So it's actually becoming cheaper with every table I buy, which is great in terms of cost, but in terms of being a constant rate of change, I don't have a constant rate of change. Instead, what I have is 8 over 1, 6 over 1, 4 over 1. This is not a constant rate of change here. It doesn't exist. So it's not linear. And again, if I was to graph this, what you would see is that my tables 1, 2, 3, and 4, while table 1 might cost me $10, okay, and the next one's 18, and the next one's 24, okay, we can see that actually it's becoming, it's going to be actually going like this a little bit, going to be kind of curving down. It becomes a little less, so it's a little curved. So it costs less money the more that I buy. So I don't have a straight line, I have a curved line. It doesn't quite work that way. Okay, so there's no constant rate of change. It's not a linear relationship. Let's look at the next one. Here we have 2, 4, 6, and 8. Now we've been doing ones where we add by 2. Okay, so let's say we look at adding 2 again. See if we can do that still. You don't always add. Sometimes you multiply, but let's look at adding here. So when I go up by 2, what's the difference between here and here? Well, 650 minus 325. I'm going to just double check on my little calculator friend here. It's been a long couple weeks. So 650 minus 3.25. Oops. 6.5 minus 3.25 is an increase of $3.25. So what I want to see is when I go up here, increasing by 2, do I also have an increase of $3.25? So to do that, I'll do 650 plus 325 and see, does that still become at the same rate? So 650 plus 3.25 is 975. So yeah, that is still an increase of 3.25. Let's try the next one. I'm going to go up by 2 again, it looks like. So is this also going to be an increase? Let's take a look. What is 9.75 plus 3.25? It's 13, so that's the same. So what we can see is that we have a constant rate of change, that every time the cost goes up by 3.25, we're buying 2 more dozen donuts. And that's our constant rate of change, meaning that the cost of donuts is not changing depending upon how many dozen you buy. It stays exactly the same. So that becomes my constant rate of change for that one there. Okay? Now, one thing you could think about here is that you are also, 2 to 4 is also multiplying by 2, right? So it does work out nicely there. Am I multiplying by 2 here? Well, 3.25 times 2 is 650. So that does work. If I think about this, what is 2 to 8? I'm multiplying by 4, right? If you multiply 3.25 times 4, well, what do you end up with? 3.25 times 4 is 13, the same thing. So as long as what you're doing is the same all the way through, you can also show with multiplication that things are going to be linear relationships. So it's not always adding, It can also be multiplication. So just be careful there. When I'm looking at the examples here, a lot of these are pretty basic and you do them with addition, but you can do multiplication as well, again, as long as you're going vertically down your table and you're doing the same thing to each side equally, right? Times 2 times 2 or times 4 times 4. You can show that it's a linear relationship. Okay, our last one here. Let's do the multiplication one. We can go 5 to 30 is times 2. That works great. Is this times 2? 2 times 2 is 4. That works great. Okay, how about 15 to 45? With 15 to 45, I can get there by multiplying by 3. Well, what is 2 times 3? Well, 2 times 3 is 6. So that doesn't work because that's a 5. So already I can see it's not proportional there. I can look at also here, I can go 30 to 60. Look at this, 30 to 60, that's times 2. So 4 to 6, 4 times 2 is 8. So that's not proportional there. So looking at multiplication, I can see that it's not proportional. Again, if you did the addition part, let's back up here a little bit just to show you that addition does work too at times. Okay, we can see here we're adding 15 and then we're adding 2. So here we add 15 and we're adding 1, not proportional. Adding 15, adding 1. But I already have a mess up right there, don't I? So this is not a proportional relationship because I have 2 out of 15 on the first one and the other ones are 1 out of 15. So that is not a linear equation. It's not going to work out. So you can use multiplication, you can use addition, okay? Just look at them, make sure you're doing the same to both sides of the table with our x value and our y value. And a constant in proportionality is y divided by x. That's what the k value is, which later on will become our slope for our lines. We'll talk about that later on. For today, keep it simple, finding the constant rate of change. And you have about a couple problems to do, not too much. So take a look at those and I'll see you back here in just a minute. Okay, constant rate of change. Looking at our homework today. First question you probably have is, what do I do with number 5 and 6 because there's nothing there? And honestly, I can't tell you because there's nothing there, so don't worry about 5 and 6 because something didn't copy quite right there. I'm not sure what happened. There probably should be some information, but I'm not seeing it, so don't worry about 5 and 6. Okay, number 1. Let's see whether it's proportional or not. So here we're going to go. We can look at addition if we want to. This is going to be up by 2. And that's increasing by 20. So here we're going to increase by 2. Is this increasing by 20 as well? Yes, it is. Increasing by 2. And 50 to 70 is plus 20. So that is indeed proportional. We would say yes, that it is proportional. And our constant proportionality is our y over x value, which is 20 over 2, which I can reduce down to 10 over 1. Or $10 for every hour babysitting. That's kind of how you think about that. So how much money do you earn? You earn $10 per hour. Okay, $10 per hour. That's how you can look at that. Other ways of thinking about it, you could look and say, well, this is 1 times 3. What is 10 times 3? Does that still work there? Sure it does. What is 1 times 5? 10 times 5 works there. 1 times 7. So you can use multiplication and see that it also works. Look at number 2. Number 2, we can look here and say, well, we're looking temperature per minute. We can see we're going up 1 minute. After 1 minute, the temperature is increasing by 4 degrees. We go 1 more minute, and the temperature is increasing by what? 4 to 8 is 4 degrees. We go up 1 more minute, and the temperature is 68 to 72, 4 degrees. So it's very constant. We have a constant rate of change. It's going up 4 degrees per minute. That becomes our constant rate of change, which is our x and our y. So our y over x value is 4 over 1, or 4 degrees for every 1 minute is our increase in temperature. Number 13. All right, we got 10 to 15, so we can say it's adding 5 if we want to, and 100 to 110 means it's adding 10. Let's see if it works to the next line. 15 to 20 is adding 5. And 110 to 200 is adding, oh my goodness, 90. Well, that's a big change, isn't it? So already we can see we have a conflict. Let's look at the last one. We add 5 there, and now we're adding 40. So no pattern. This part's all wonky, all messed up there. So there's no constant rate of change there, right? So there's no k value because we have 10 over 5, 90 over 5, 40 over 5. There's no constant rate of change for number 3. And our last one, we go 5 to 10. Again, we could look at it as adding or multiplying, however you want to think about that. We're going to go to add for now, so adding 5. In this case here, we're adding 20. Here we add 5, and 20 to 50 is adding 30. That's not right. Adding 5 there, and here we add 20. So you can see the difference there between here and here and here and here means that we don't have a constant rate of change, right? We have 20 over 5, we have 30 over 5, and 20 over 5. So I'm not going to get a linear equation out of this one here. It's going to be a little curvy, so I do not have a constant rate of change for number 4. All right. Again, just get an idea of how you figure this out, looking for that constant. It'll make a little more sense as we look at slope next, but remember that this is essentially our dependent and our independent variable, independent and dependent variable, and how we get to create slopes with lines and things like that. And that's it for today. Have a great day. We'll see you next time for some slope.